but that's all right. Uh, we'll survive. Jack, hope you're doing good this morning. Um, so, all right, let's remind ourselves where we were last time. We were talking floating point. So let me pull back up the little thingamajig, and I think I put this in documents here. Okay. Okay, so let's see, just to remind ourselves where we were, the encoding, right, for a single precision float, one sign bit, 8 exponent bits, 23 mantissa bits, and they're in that order: sign, exponent, mantissa. So the mantissa bits are the lowest uh, bits in terms of memory address, and the sign bit is the highest bit in terms of memory address, right, because of the Indian problem. Uh, and the thing, just to keep everybody on our toes, right, is that the exponent is biased by, for a single, 127, and for a double it's biased by 1023. Okay. Um, yeah. So let's see. I think where we left off was we started talking about, okay, what registers do we have for floating point on our hardware? Well, we've got, basically for now, let's just treat it as there are D registers. There's 32 of them, just like the X registers. They're 64 bits wide. Oh, good morning. Yeah. They're 64 bits wide. They hold double precision things. And like with um, like with the X registers, the lower half of the X registers we call W's. And same thing here, the lower half of a D register is an S register for single precision. And it turns out that you can actually further subdivide these guys into half precision or bytes. And truly, they all sit inside 30, the V registers, which are all 128 bits. That allows us to do, it's not that we would use those for quadruple precision stuff, but it allows us to make vectors of uh, other things. And we'll see that probably next week when we start talking about SIMD, which is how you accelerate floating point computations. Well, really any computation, but floating point specifically. Uh, Right. Okay. So that's what we got. And the operations that we have, most of them are exactly the same as with integers. And the ones that aren't have a, mild update, namely usually the letter F at the front. But um, okay, so most of that's going to work pretty similar. We've got addition, fuse, multiply, addition, the sort of usual stuff. But we just have to say, hey, do it with floats rather than with X registers. So that's pretty straightforward. We also have comparison. There's other things like square root that are built into the thing. Um, and I think we talked about, okay, what do you do if you don't have a square root thing? Well, you can build it by doing a uh, Taylor series or Newton's method or some other numerical approximation scheme that you guys learn in, um, in calculus or something. So, okay, so let's go through and I'm going to pull up here uh, the the textbook gives an example for how to compute uh, the sign of a number, and it does it using, it gives two examples. It gives a 32-bit and a 64-bit um, version. And where is, sorry, I'm just looking for my, um, there it is. my notes here. Okay. So let's actually just do some programming here. So let me open up Genie. Let's close this project. And we'll call this sign single. Oops. And then let's save this as, say, sign.asm. Okay, so the first thing we need to do is we need coefficients, right? So the whole idea behind, let me just put a comment in here. The whole idea that we're going to basically be using is that okay, so that's the whole idea that we're going to be using is that, in fact, just for the sake of starting, let's just program it with exactly what I've got there. Uh, a fifth order Taylor approximation. Okay, so, um, all right, so what makes it fifth order? We went up to degree 5 in our polynomial. And where do these coefficients come from? The 1 over 3 factorial, the 1 over 5 factorial. These things come from Taylor's theorem in calculus. Basically, that the coefficients are related to the derivative of the function and its value at 0, and then there's a factorial in there just to keep it spicy. Okay, so this thing here, fifth degree Taylor polynomial, we could keep this game going all day long, right? And you guys can guess here probably what the pattern is. What powers appear? Only odd powers. What's going on with the coefficients? Two things. Huh? Yeah, they're the odd factorials, and what else is true? Yeah, they alternate negative positive. Okay, fine. So great, we've got our Taylor polynomials. Wonderful. Um, okay, so what we need to do is we need to program in those coefficients somehow. Okay, and uh, so what is 1 over 3 factorial? Well, in this case, that's just 1 over 6, right? Because 3 factorial is 6. All right, so what we need to do is we need to encode here 1 over 6 in the floating point format, okay? So how are we going to do that? If we don't do it by hand, what do we do instead? Well, if only there were a little toy that we could use. Right, Evan? Okay. All right, float toy. So we're doing singles here. What number do we need to encode? 1/6 with just a decimal is that. And notice, by the way, that if you go past a certain number of decimal digits, it doesn't actually change the floating point encoding because you can only go so far with 32 bits of precision. Okay, so what do we get here? 3E, 2A, AA, AB. And, oh, what did I mess up though? What do we actually need here? Negative 1/6. So let me flip the sign bit and we get this, okay? BE2A. Huh, interesting. Um, so the book actually has an A for that final character, meaning that it didn't round that final digit to a 7. in decimal, but that's okay. We'll just use this as our approximation, okay? So that number is what we need to do, and what we're going to do is we're going to define a table of these coefficients, okay? And so that's um, uh, the first one, or really the second one, right? Because what's the first one? Just one, so I don't really need to bother encoding it. Although we certainly could. So why don't we actually just throw it in there just for sake of completeness? Um, so what is ones encoding? Well, makes sense, right? Because what's the sign bit? 0, because it's positive. What's the exponent going to be? Well, 1 is 2 to the 0 power, right? So what should the exponent be? 0, but how do we encode it? As 127 because of the bias, right? So the exponent is exactly 127, which is 0 followed by all ones. And then do we need any manticipits here? No, because there's nothing after that 1. All right, so we got 3F8, 0, blah, blah, blah. And all right, so let's copy that in there. And we don't really need to do that because multiplying by 1 doesn't do anything. And it will actually spend an operation on that, even though we don't need to, but that's okay. This will just be sort of for good completeness. Uh, and then we need to do the same thing with the 1 over 5 factorial. What is 1 over 5 factorial? Well, it's 1 over 120. Okay, let's put this in decimal. All right, so there it is as a decimal, right? So let me take that and put it in our float toy, and then we get this guy, and then we just need to put the 0x in front, and let me compare that and make sure that Dudebro agrees with those. So what do we have? Uh, did we get that right? Let's just double check against the Google. That is not what we got when I did it in here. Um, hmm. Okay, I'm not sure why it gave us that. So it's a good thing we double checked it because, all right, so 0.08 and then a bunch of threes is actually what we wanted. Oops. Huh? 3C 08. Yes, okay. And now we agree with the book. So, all right. So if we had done that, we would have had a terrible approximation. Although, yeah, okay. So there's that, and then couple of things here. Well, how many terms have we put in? We've only put in 3 of them. Okay. And then I don't know if we really need this, but the book does this sort of thing. So um, let's just do this. Um, that. Okay. I'm not entirely sure what that does, but we'll just throw it in there. Okay. And then we need our text section. Oops. And then he says align 2. Okay, and then now we're going to have our code, right? So what's our code going to be? Well, we're going to need to use a main routine um, because so when we use GCC to do the linking, GCC, because this is the way C is, expects there to be a main routine. There is another way to link it without using GCC, but I find GCC is just such an easy tool, and we use it a lot anyway that we'll just do that. Okay. All right. So we've got our global main function, and then let's get into the programming. What is our main function? Well, okay. What do we got to do here? Huh? Math. What do you mean? Oh, MAD. Yeah, yeah, the fuse, multiply, add, right? Okay, so what we need to do is we need to load, well, first off, if we need a value of x, right? The whole point here is to compute the sign of something, right? So we need to accept from the user what we're taking the sign of. All right. Well, if we're going to do that, how do we do that? We need a string. We need several strings probably, right? So, right? So we need a string, okay? We need a format string for the input. All right, so what's our format string going to be here if we're accepting floats? Yeah, it's %f, okay? Um, okay, and then that we can also use as our output string, uh, or we could just say this. Uh, let's do this. ASCII, the sign of %f is %f. And then let's do a backslash n. Okay, so that way we can put in what the user input as the first %f and what the output value of the function is as the second %f. Okay, good. All right, so now what? Let's go down to our main function. Well, what's the first stuff we've got to do? What's the very first and very last things we need to do? Yeah, we need to do the stack stuff, right? So the first thing we need to do is store pair x29, x30, stack pointer -16, exclamation. And then at the end, we need to load the pair, pop it off, right? And then we need to load in a return condition to the OS and return. Okay, so got to have all of that. What else do we need to have here? Well, I've got to do the user input. Huh? Right, so I got to bump up the stack again to make room for the user's input. Okay, so let's do add stack pointer -16, and then down here to compensate 16. Okay, so the stack has been expanded so that we've got room for the number. Yes. So if I add -16, that's the same as subtracting 6, right? Now, about that. this time last year, I spent 3 hours at Starbucks trying to debug why I was having a program that segfaulted, okay? And it turned out that everything was fine except I had right here at the very beginning sub SPSP minus 16. So what it was actually doing was adding, and yeah, there were goodbye 3 hours of life. And then when I finally found that, I was just like, yeah, I was furious. Okay, but that's assembly, right? Um, yes. So this is why you don't do assembly after midnight, because I mean, I don't think any programming after midnight is ever effective, right? Good luck finding that missing curly brace. Okay. All right. Anyway, so we've expanded the stack for the user's input, and now we actually need to get the input. And now the floats, right? These are 32-bit things, right? So I've had to expand the stack, and I actually have room and memory for 4 of them because we're going to do the single precision version here rather than double precision. Um, and so what this means is that I've got room and memory to store the user's input, but also the output while I'm at it. Might as well. Okay. All right. So let's take the um, let's get the user's input first. Okay. So what do we got to do? We've got to move to X0 the address of the please string, and then what do we need to do? Tell the user, hey, please type something. Okay. Then what else do we got to do? We got to move X0 the in string, and then we need to branch and link to. Oh, what else do we have? What else does scanf need? Yeah, we need to tell it where to put the data. In this case, it's right at the bottom of the stack, so we need to move X1 to have the stack pointer inside, or a copy of the stack pointer. Then we can branch and link to scanf, and now when we come out of this, the number that was input is sitting at the 4 bytes starting at stack pointer. So it's sitting at stack pointers plus 0, 1, 2, and 3 bytes. Okay, so because 32 bits. Yes? Okay, good. So now let's start doing the math. Well, um, what kind of math do we need to do here? Well, we need to take the data that's sitting in um, sitting on the stack, and we need to load it into a register so we can start doing computation with it. Okay, where is it on the stack? We just said it's right at the start of the stack pointer. Okay, so that's easy. But where do we want to move it to? We need to get it out of memory and into a register. Which register? D, S, X, W, S in this case, right? Because we're only doing single precision. Yeah. Um, okay, so we need to load the register S0 with the thing that's sitting at the stack pointer. Okay, not X0, because X0 would be to treat that thing as an integer, not as a float. Okay, good? Huh? Well, just wait until later this class, my friend, as we get to look at my favorite algorithm of all time. Okay, so got that in there, right? And now we need to do, we could do this with a loop. All right, and the book does have it with a loop. Since we only have 3 terms, let's not bother with the loop. But what's the form that we need to get this stuff into, right? So if our approximation is in this form, right, that's the Taylor polynomial, how would I reformat that so that I can do this with fused multiply add? Right, so what's the whole trick of Horner's rule? Hmm? Well, let's just think, right? It's going to be 0 plus x times 1 minus what? 1 over 3 factorial x squared. Um, okay, I think I may be screwing up the parentheses here. Times, well, you know what? Forget it. We'll just, they do it that way in the book. We'll just do it. We'll just do it. Okay, so what's an S0 right now? It's the number x, right? What do we need to multiply x by? 1, right? And we need to add it to 0 because we don't have anything. So why don't we make S0 hold the number x? Sound good? And let's make S1 hold our approximation. So we'll continually add things to S1. All right, so the first thing I need to do is I need to clear out S1 because who knows what's there. And so I need to move the value 0 into it, and I'll just type 0.0 here for just to make sure that we're clear that it's a float, right? Okay, so what do I need to do first? I need to add x to this to that register. Okay? What else do I need? So what other powers of x do I need for the particular approximation we're going to do? I need x cubed, and I also need x to the fifth. Okay? So let me do this. Let's put x cubed, let's put x squared in S2. Okay? All right, so this will, oops, okay. Okay, is that all right? So I'm just computing the powers here. Okay, and then now I just got to put the coefficients in front. Okay, so what should the coefficient of S3 be? Or the coefficient of x cubed, sorry. Yeah, it's our second thing out of our table. Okay, so how can we get the thing out of our table? Well, we could get it directly, or we could do some offset business. Okay, so what about if I load, or sorry, let me move x0. Let me put 1 there. Okay, and what I'm going to do then is, so I need to get the second entry out of my table, right? And so what I want to do is I want to load, actually, let me put this in x1 and let me put in oops, dang it. Let me put in x0, and actually I want the load here. I want the address that the table starts at, okay? So if that's the address that the table starts at, then um, what do I actually want to put here? So what's one entry down from the first entry? It's one entry, but how many bytes over is it? It's over 4 bytes because this is 32-bit data. All right, so what do I want here? I actually want the number 4, okay? Because I'm going to use x1 as an offset. Yeah? Okay. All right. So let's. So what do we need to do? We need to get that value into an S register, right? So what am I going to do? I'm going to load S. Well, let's say S5. Okay. With what? Data that's coming from where? X0's address offset by X1's value. Okay, so now S5 should have that value in it. Okay. Huh? Oh, sorry. Yeah, sucks to suck. Okay. So now, did I have to actually write it that way? I could have just literally hard coded this and said load S5 pound 0x blah blah blah, right? But since we've already written the coefficients in a table, we might as well take advantage of that table. In particular, if we wanted to be a little bit smarter about this with using fuse multiply add, then we could do it so that this was a loop, and therefore we could, if we wanted to do this for a higher order number of terms, we just need to put in more coefficients, but the code wouldn't change. Okay, here we're kind of hard coding it just to get a sense for how this thing works. All right, so now that we've got 1 over 3 factorial in there, what do we need to do? Oh, and what have I messed up here? What should all these things be? F. Oops. Right, because those are floating point operations, not integer operations. Okay. All right, so what do we need to do? We need to multiply S5 and S3 and add that to S1, right? Okay, so what's the fused multiply add? S1 is the destination. S1 is or sorry, what are we adding to it? Well, whatever S1 is, right? Okay, plus S3 times S5, right? Okay, so let's just make sure that that syntax is correct. So what's the syntax for the fuse multiply add? Multiply the last two things, add the other thing, and then put that in the destination at the very beginning, right? And I'm using S1 here as an accumulator, right? So it's going to accumulate our total as we go. Huh? All right, well, let's just double check that I didn't screw up the syntax. I mean, we'll know it if I did, right? So, okay. Nope. Destination, thing that gets added, the thing that's get multiplied. Okay. I know. What's the horrible thing? Well, okay. We'll know if it's screwed up because we can compute the sign of something. Well, that too, right? Is that we can step through it in GDB and see where the number starts to get funky. Okay. All right. So the next thing I need to do here is I'm going to add, not F add, I'm going to add 4 to x1, right? Because it's my offset thing. Okay, so now x1 is 08, which means the next operation I'm going to do, I'm going to load S. Well, does it matter where we put it? Let's just put it in S6 so that we could step through this. And then we're going to do another fused multiply add. S1 is the destination. S1 is the dude that gets added, but this time it's going to be what are we multiplying? S4 and S6. Okay, and that should be it. Okay. All right. So questions, preguntas, fragen. Well, why not? Just to make you learn the. No, I mean you can type in 2.5 or whatever, and it'll do it for you. But the I guess part of the benefit is just forces you to learn the encodings and figure out how to encode a given number. So, yeah, and in fact, to some extent, the version that's in the book does sort of a Horner's the rule kind of thing, right? So it would have been a pain in the butt in the sense that we would need to think through, okay, exactly where, like, how do we format it for Horner's rule, and what are we going to put where? Um, just for the sake of demonstration, well, that and I didn't want to just sit here and type what's in the book for you guys, right? Like you guys can do that. You can read the book. You guys aren't idiots. Uh, so I just want us to get a taste for how this floating point stuff is working. Okay. All right. So um, we're basically done, except so where is our answer? Sure. Go ahead. 1/3 factorial? No, we don't. So we could have put that in S5. Right. Which for a loop would be exactly what you want to do, right? I deliberately put it in S6 here so that if we step through in GDB, we won't destroy old data and we can kind of see how it's computing. But yes, for efficiency's sake, we could be a lot better here, right? And in particular, did I use a loop? No, I should have used a loop, right? If I wanted to be efficient. Okay. All right. So now S1 has our answer in it. Okay. And S0 still has the original number that was given by the user. So now we just need to print those things. Okay. So what's going to go into X0? What did I call it? Sign string. All right. And then what do I need to load into S1? Or actually, I don't need to load anything into S1 and S2. Or sorry, S0 and S1. They're already there, right? Yeah. Okay. So can I just branch to printf now straight away? Yes. Should be able to. Okay. And then I've got a bunch of white space here. So let's get rid of that. Okay. Sound good? All right. So we need to assemble it, make sure I didn't make any stupid typos, and then we'll run it. All right. So let's get our terminal open. All right, so we need to go to let's see, what did we, oh, those should have been load instructions, not, all right, so where was that? This should have been LDR, and this should have been LDR. Okay. Must be a SIMD vector element. Okay, what did I mess up there? I've messed up the load immediate. Let me just double check that I haven't screwed up the syntax. Oh, it should be fmove, right? Okay, so we need this should be fmove, but the others are okay. Okay. No, invalid floating point constant. Huh. Well, maybe it doesn't like the decimal point. Yeah, that does kind of defeat the purpose of the fmove. Okay, so let me make sure I'm not being a complete moron here. Which at this hour of the morning is, of course, entirely possible. I could have sworn you could have just done that. Load store instructions. Huh. That's interesting. Okay, well, maybe it wants to be picky. Why don't we try... That's the encoding of 0. What the heck? Okay. This doesn't make sense. Floating point constant at operand 2. Okay, why don't we just try 1.5? Right, that's not what we want there, but okay. All right, you know what, computer? If you're going to be a pain, then I'm going to do this to you. Fine. Deal with it. Okay, I don't know why it's being ornery about that. That doesn't make any sense. Okay, so I just loaded 1.5 and immediately subtracted it from itself. Screw you, assembler. Okay, so GCC. Let's see, we need sign.o, output sign, and then let's run it. All right, please enter an angle in radians. All right, let me do pi halves is basically 1.57. Or actually, you know what? Let's put in 0 first, because what should we get? 0, right? All right, makes sense. All right. Pi halves, right? Sign of that is 1. Womp womp. Okay, well, Back to the old drawing board, as they say. Well, okay, so let's um, let's pipe it through the GDB and figure out what's going on, right? That's why we have this thing. All right, so I need to reassemble it with the dash G to get the debugging stuff. I need to I'll go ahead and do static so that we don't croak on printf and stuff. All right, and now we can do GDB sign. Okay, break main, and let's start stepping. Oh, run first. Okay. All right, so let's uh, let's go through a little bit here. Okay. All right, so let's do. Oh, right. It's not going to show us the S registers. How do we get those out of GDB? You know, I'm not actually sure. Um, well, let's find out, shall we? All registers. Okay. Was there a dash? Okay, yeah, this is really helpful. Right. Okay. But let's well, okay, so don't freak out, right? But like look, what do we got? We've got V0. Okay, there we go. All right, S0 has uh there 1.57, right? As a single precision thing, and that's I guess it's encoding uh in hex, okay? I am not sure. I guess unsigned and signed maybe, or like treating it as an integer. Not sure. Um, huh? Yeah, that's this thick, right? So, okay. All right. Well, whatever. So let's see if we can, I wonder if we can do this. Um, nope. Hey. Okay, that's much nicer. Okay. Huh? Probably. Nope. No, there is a way to do that. Like it says here, there's like reg group, and so there must be a way to group those things. I wonder if we can actually do. Nope, can't do that. Okay, but that's okay. Right now, all we care about is what's in S0. Okay, and then oh, also while we're on the subject, we do care about what's in S1. I loaded 1.5 in there because the assembler was being a Patuki. All right, and then I immediately subtracted it from itself, and now it has 0 in it. Okay, good. All right, so let's step. Okay, S0 squared. Oh, I haven't actually run that yet, so I need to step first. Okay, there we go. All right, 1.57 squared is 2.46, blah, blah, blah. Okay, so we're looking good so far, right? Um, well, let's just step a few more times. Okay, so so we need to do what is in register. We need to look at registers 2. We just did that. S uh, S3 has that's 1.5 cubed. Okay, so we're good there. And S4 had that thing to the 5th. Okay, that also looks reasonable. Okay, all right, so we're good there. All right, so I load number 4 to X1. Okay, so S5 after this instruction should have, okay, looking good, subject to some rounding. Okay, add X1, X1. Still, it's still, oh, okay. No, no, that makes sense, right? Because what have we done? We did this operation right there, right? So S1 has, um, uh, it has X plus 1 over 3 factorial, well, X plus negative 1 over 3 factorial times X cubed, right? And uh, that seems too big, doesn't it? Well, okay, S1, if we go back up a little bit, right? S1 was the number X. Or sorry, S1 was 0. I started at 0 to be my accumulator, right? Okay, so it should have been, um, um, okay, S5 did correctly have the coefficient, right? You know, I bet you, I wonder if you're right that we actually have this in the wrong order. Let me just double check here which is what we've got, right? Or S3, sorry, the 5 point whatever, right? All right, so let me just double check the fuse multiply add to make sure that we've, nope, you're right. You're right, we've got the wrong order. So it should have been, so let's go back up into our code. It should have, for the fuse multiply add, the guy that gets added is at the end, not at the beginning. Yeah, yeah. Okay, so that we only used a fuse multiply add twice, so that should be okay. Um, yeah, I'm not sure. All right, let's just recompile it and see if that fixed it. Okay, that part still is okay. All right, well, yep, another 3 hours at Starbucks. Well, okay, it also is actually, you know what has to be the case here? Like, it's not even correctly printing our first value, right? Because I entered 1.57, but it's okay. So why is that happening? I guess is the I should be, yeah. I mean, because it should be printing from S0 and S1 the same way that, I mean, unless it doesn't, well, okay, here's how we figure that out, right? Let's, no, well, forget Google, right? No, no, they're physically separate. But the format string with %f should tell it to print a float, and so I don't know why it's not going. All right, so let's do. Well, we could move the bit pattern, but it's going to print it as if it's an integer, which is not what we want, right? It'll look all crazy. All right, so what? No, because the address has to go into X0, the address of the string, right? Oops. Okay, so here's how we test it, right? Let me just, oh, and I've got a extraneous parentheses there. All right, so I just define a float x 1.57, and then I'm going to print it. Oh, yeah, thank you. Okay. Is it include or import? Oh, yeah. I always forget. Oops. Thanks. Okay. So it is %f. Now, here's the real test, right? Is we want to do this. Okay. And then, which is, okay. Well, yeah. All right. Well, let's see what it did, right? Okay. So, blah, blah, blah. I do see a printf. Okay. S0 has the number. Okay. So, what have we given printf? Um, oh, right here. This line right there. Okay, good question. Well, what do you think it does just looking at what the registers given to it are? It's a float because we've got an F in front of the opcode. That makes sense. But what else is going on? What it's doing something involving registers D0 and S0. Well, you don't know what CVT is. Circumvent, convert. Uh, it's the almost the airport code for uh, Cincinnati. CVG, Covington. Yeah, yeah. You don't have all the airport codes memorized? Yeah. Okay, so what does it look like it actually did there? Is it looks like printf here doesn't want things in S's, but rather wants them in D's. Okay. D is bigger. Okay. But what kind of floating point number does D hold? A 64-bit double. Okay. So this FCVT is floating point convert. So what it's doing is taking a 32-bit float and extending it to be a 64-bit float. Now we don't get any extra precision out of that because it was all like it started in life as a 32-bit thing. Okay, so what based on our little test here, what do we were almost there. We were just trying to make printf. It was loading D0 and D1, but what was there? Yeah, okay. So, all right, so let's try this again. Let's just go into here and, well, no, not change everything to D's. Right here, oops, let's convert our S's into D's so that we can print them. Okay, so let's see if that works. Okay, that still works. There, now it works. Okay. Yeah, so we had two mistakes here. It's the order is the two things you want to multiply, then the thing you want to add, and the very beginning is of course your destination. Okay, so I had it wrong in the PowerPoint. Um, and destination to multiplier multiplicand adder. Yeah. Okay. Okay. So sine of 1.57 is 1.004 blah blah blah. Okay, it's a little bit off, right? Right. It should be one on the nose. Why isn't it one on the nose? Well, two reasons, multiple reasons. It's a numerical method, right? I only did a fifth degree Taylor approximation, so I shouldn't expect to get exact answers. That said, the closer I am to zero, the better these approximations are, right? So, for example, what is let's do like pi over 6, or even pi over 4, right? What is pi over 4? What's 1.57 divided by 2? 0.75 with a little bit of chump change. Okay. All right. So 0.75, right? If I run this, right, I get 0.68 blah blah blah. All right, so 0.75 is close to pi over 4, right? What should I get for sine of pi over 4? Root 2 over 2, which is 0.707 blah, 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 right? Are we pretty close? Yeah, subject to two things. One, pi quarters is not 0.75, it's 0.7 blah, 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 blah. And two, this is only an approximate method, it's not an exact method. Okay? All right, so TLDR, what did we just learn? For printf, what kind of floats can you print? D-register doubles, that's it. Okay? Which means if you're doing single precision computations and you want to print them, then you need to extend, convert, right, with the FCVT thing. Okay? That actually is a good lesson for something that we're going to do next. And yes, okay, so let me go back to the spreadsheet, I mean, this thing here, right? All right, so this we had wrong. It should have been DN, DM, DA. Okay, so that's corrected. Um, Okay, so we just did sort of a variation on the book's floating point routine. We did it in single precision. The book gives looped versions, which is better, for both single and double precision for sine. They also do a few more terms of the Taylor polynomial, which means that they get slightly more accurate answers. Okay, and you guys, we'll continue exploring this stuff with sine, because we'll do. He also gives examples for how to do this with the SIMD instructions, which is where we start using the vector registers, because then we can speed this thing up quite a bit. Okay. All right. I really want to start talking about this because I want to blow your minds. Okay, we already talked about the square roots. All right, so we talked about how you can approximate the square root last time using Newton's method. Okay, that's one method of doing it. You could, if you wanted, also cook up a Taylor polynomial. Okay, but what about if you wanted to do 1 over the square root? Well, one thing you could do is just approximate the square root and then do 1 over that. Okay, that'd work, but it's slow. Okay, so programmers never live in a vacuum, right? You learn things by seeing how other people did it and then tweaking it, right? So the solution is to look at other people's source code. Okay, so the following is a piece of source code. How many of you guys have ever played Quake 3? You guys are too damn young. Yeah, get off my lawn. Okay. Huh? Yeah, yet. I mean, I'm 37, almost 38. Fortunately, you'll be graduated, huh? Yeah. Well, I mean, I turn 38 next month, so. Um, all right. So here is the source code. Let's just take a look at that. It's fine. No, because x2 you use down here, right? Oh, you're right. Actually, I never noticed that. Yeah, whatever. Okay. So what's my favorite part? Favorite line of this code? Yeah, the one where it has the comment, "What the fuck." Okay, this is actually in the source code. Okay, I'm not making this up. Okay, but let's look at what on earth is he doing here, right? Hmm? No, no, no. This is in the original source code. This is not my comment. Okay, I know what he's up to, but yeah, it's doing a bit shift. Okay, so here's what's happening. We're taking the original number, okay, which was y, and we're converting it into an integer. Okay, now when I say converting it into an integer, let me be careful. I am taking its bit pattern and just pretending it's an integer. Just, yeah, I know, WTF indeed, right? Just trust me, okay? Do that. Bit shift it by 1 position to the right and subtract it from this number that came out of thin air, okay? And then then convert it back to a float. Let me demonstrate this. Okay, so I'm going to do 1 over the square root of 2. Okay, and the reason I chose that is because 1 over root 2 is the same as root 2 over 2, and I know exactly what that number is. Okay? All right, so first step, right? 2 as a 32-bit floating point number. It's that. You guys can trust me on that, right? Okay, second, pretend that it's an integer, not a float, and shift everything 1 bit over. Now, not shockingly, if you do that, that gives me the new value here. Okay, so I just bit shifted it. Okay, as integers, subtract that from the magic number 5F3759DF. That gives me 3F3759DF. Okay, 1. Take this bit pattern. Pretend now it's really a floating point number. Decode it, and what do you get? 0.7162151. 7162151. What's this answer I'm supposed to get? 0.707 blah blah blah. That's pretty damn close. Wow. This is magic. Okay. All right. So now the second part of the source code is so how does Newton's method work? Newton's method requires that you have an initial guess for the approximate value of your answer, and it improves the accuracy of your guess, right? So the trick here is not using Newton's method, but how to produce the initial guess. And that's where we have the magic number. Huh? Yeah, the predictor part is the voodoo. Okay, so pipe it through Newton's method and improves the approximation enough for the purposes of Quake 3. Let's go back to the source code here. You'll notice that he commented out a second iteration of Newton's method because it wasn't necessary for the accuracy within the game source code. He could have done another iteration, but it wasn't necessary. Okay. And so that's why it's commented out. It's interesting he commented it out rather than just deleting it. But yeah. Okay. Now, isn't that like cool? Well, yeah, we can get pretty close by doing what on earth did we just do? Yeah, okay. Yeah, pretend it's an int, do something, then pretend, oh, it was really a float all along, right? Yeah? It comes in as a float. Right. Huh? Well, because the bit shifting operation is not something you can do on floats, right? So you have to do typecasting here. Ah, that's the best question. Thank you, Mr. Lillis. Where did the magic number come from? Huh? I've got a couple of papers for you guys that you can look at to see why the magic number is the magic number. Huh? No, like papers for you to read. Not too many. 2 digits, not 3 digits. Okay. All right. Right. All right. So there we go. We'll continue with the discussion of the WTF stuff next time. So, and then also SimD. Yes. All right, let me kill the stream.